For our next example, let's see how a mapping rule can help us determine the graph of a radical function. Here, we're given f of x equals negative 3 times the square root of x plus 5 plus 6. We can determine that there's been only one horizontal transformation here. That is a translation of 5 to the left, so x maps to x minus 5. Vertically, we've had both a reflection in the x-axis and a vertical stretch by 3, and then we've had a translation 6 up. So we'll show that as y mapping to negative 3y plus 6. This is really helpful because now, in order to create our graph, we'll refer back to our basic radical function and simply apply this mapping rule to some of the points found there. Remember our points of 0, 0, 1, 1, 4, 2, 9, 3, and 16, 4, the perfect squares that we square rooted? Well, let's see what happens to them when they go through this mapping rule. We'll see that each x value is subtracted by 5, while each y value is multiplied by negative 3 and then increased by 6. Our last transform point of 11 and negative 6 didn't fit on the graph, but you can see that it's about to reach that point. Now, in order to determine the domain, remember, we just need to find which values of x make the radicand greater than or equal to 0. So let's take that x plus 5 and compare it to 0. Subtracting 5 from each side, we quickly find our domain. Our range we think of graphically. Now, if we can think of the parameters of a, b, h, and k, where k is our vertical translation, we can see that the 6 will be the upper or lower limit of our range. And what determines whether it's a lesser than or greater than symbol is whether we have a negative a value, which is just to say that reflection. Here, because of our negative 3, our whole graph is going to be below or equal to 6 rather than above or equal to 6, which it would be in the untransformed graph. Intercepts are all about replacing with 0. So when we want to find our x-intercept, we replace y with 0. We subtracted 6 from both sides and then divided by negative 3. And then we squared the 2 as we squared the square root side. I found in the past sometimes students get nervous when they get a negative answer because they say, I thought x had to be positive. Remember, x doesn't have to be positive, just the radicand has to be positive. So as long as that negative 1, when substituted into the x plus 5, keeps the square root having a positive radicand, or 0, you're okay. Now we'll find the y-intercept by replacing x with 0. This isn't really a situation of solving so much as evaluating. So when we get to this negative 3 root 5 plus 6, there's nothing more we can do. We could evaluate it to be the nearest hundredth, in which case we'd get approximately negative 0.71. This next example is functionally equivalent to the one before it, but because we've given a b value for a transformation instead of an a value as a transformation, students often have more trouble with the mapping rule. Remember, when we write a mapping rule, we are writing what would happen to the graph. So here we have a b value which is negative and is 2. When the b value is 2, that is a horizontal stretch by 1/2. So in our mapping notation, we should see a 1/2 instead of a 2. Also, because the negative sign is already factored out of a bracketed x minus 8, that 8 will represent a translation of 8 to the right, as though h were positive 8. take a second to confirm that you got the same mapping rule before moving forward. Now, we'll go ahead and apply this mapping rule to our 5 basic points of 0, 0, 1, 1, 4, 2, 9, 3, and 16, 4. Notice that our endpoint here is at 8 and negative 2. So graphically, we can already see that our domain is x less than or equal to 8. Let's see how we'd find that algebraically. We write our radicand of negative 2 times x minus 8 and state that it must be greater than or equal to 0. We don't want to try to use what we know about the graph to shift our algebraic process. We always write radicand greater than or equal to 0. As we develop that left side, we get a negative 2x plus 16 greater than or equal to 0. And here we have a choice. We can either subtract the 16 from both sides or add 2x to both sides. I'm going to add 2x here. And as my next step, we'll divide both sides by 2. Remember, if I divide both sides by 2, it would read 8 greater than or equal to x, which said backwards is x less than or equal to 8, which we've written here as our domain. We'll continue to determine our ranges graphically. We see that the graph is above or equal to the endpoint of negative 2, and write that in the range. Common theme with intercepts, we're using values of 0. So for our x-intercept, let's set y equal to 0 and solve. To find our y-intercept, make x equal to 0. And there you have it.